All right, so first thing I want to do is I want to get out your graphing calculators. I want to show you how you can do a table on the calculators efficiently and effectively for limit purposes. Show you some good stuff.
I didn't get it.
If you don't have one, just kind of partner up with somebody that does. Is something you're going to want to have though. You're going to definitely want to have a graphing calculator.
No, I'm talking about homework on mine.
It didn't show up for you?
No, it didn't show up for me.
What? Let me see your.
Yes.
Know a lot of this. You're going to go to y equals. You're going to define y1 as this function. Do you know how to get to? You know the shortcuts how to get to the fraction view, the fraction template? Good. Some of you do. Oh, you have so much to learn about these calculators. I bet this is going to be great. You're going to learn a ton. You go alpha y equals 1. And then we're going to go square root x
You might need to update
minus 2.
Because it did it last year.
Yeah. Wait, you have things running around in there.
You're right.
Okay, we good?
You lost your fraction.
Everybody
Is
got
there
it?
another way to do it if the alpha y equals is not working?
Yeah, just you don't. Oh, I know why it's not. Come here. I'll tell you why it's not. You're
It was
in.
last year in this year's.
You've got because you're in a program. I'll show you a trick on this. Come here.
With the smart.
You're in transform. So what you want to do, you want to turn that plot off first of all. That was SB off. And then you're going to go to same thing.
Yeah.
Same thing. So you want to go to. I haven't done this in a long time. Apps. I think you can do any one of these. I think you're in transform. So just go to like inequality. Do it this way. If you go to inequality, there's probably an easier way, but this is how I know how to do it. Go to inequality and it's going to say quit transform. Right, so we want to do 2.
Oh, mine says quit in equal. So should I?
Oh yeah, that's it. So that's the one you were in. Yep, quit that one.
Okay.
And then now we're in inequality, and so we want to quit that. So we go. Oh, how do you get out of the pro? I think you go
So quit, I know, second mode.
Okay, mine shows up now.
second mode. No, but there's a way to get you out of the program. Go apps. Oh, this is the part I can't remember. I go home. See, it's still showing up. Darn it, how do you get out of the... Okay, does anybody remember how to get out of a program in here?
Exit. Second.
Where's exit?
Quit. Second mode.
But that doesn't, I'm not seeing the programs listed.
Oh, I don't. What are you trying to do?
Because if you're in inequality, how do you get out of it? Here's one way to do it. Go like this. Just go. You can go apps and go down to inequality and exit. Quit. There's got to be a way to get to that easier. Okay, now you're good. Yep. Now you're good.
Thank you.
Okay. Okay. So once you're in there, now you're going to go table. But we're going to do table set first. So we're going to go down to second F2 for table set. And it says table start and delta value. Those are important. So let's start at we're approaching 2, right? Oh, we're approaching 2? Approaching 4. There we go, approaching 4. So let's pick values that surround 4. We could even pick 4 if we wanted. Pick 4. And the delta value, if we go down, that's telling us how far apart are the points that we're evaluating on the table. How far apart are they going to be for x values? So let's pick something small. Like let's pick 0.0001, how about? Okay, and then we're going to go second table, and look what it does. Now we can scoot up. That's pretty cool. It says error, right? It says error, but what do you notice? I mean, we're within, to if we go out to 4 places, these all round to 0.25. We have to go a long ways probably before it doesn't say 0.25. It might be, let me go to my mode. No.
Like, I just have to go that far.
Yeah, it's only 3 for
I only have 3, I have to
We
go
only have to go
before
to
it.
4.0004.
You must have, did you go, you must have gone 0.001 for yours then.
No, 0.00.
0.0001.
And you only have to go a few places?
Yeah.
Well, that's kind of weird.
It might be because, like, with ours, see how you have multiple tables over? With ours, we only have 3, and so, like, we only have 3 columns, and you have 5 up
Yeah,
there.
I don't know. I don't know why. It must be, maybe it's a precision thing on mine.
Yeah, I know. But after that, like,
2.4. 2.24999.
Okay, so here's another thing though too. So let's just say, let me get your attention up here please. So let's say we had to get this to the nearest thousandth. We had to figure out what it was. One thing you can always do is you can force, if you go into mode, you can go down and force your calculator to go out to like 4 decimal places. Right now it's in float, but if I go down and I turn that to a 4, hit enter. Now if I go back to the table, see what it does?
oh, nice.
Okay, then it's automatically going to round everything to 4 places. Okay?
Now I have to.
Yeah, now I have the 0.25.
Right.
A billion.
Okay, does that make sense? Now usually, if you do that, I'd put it back. Usually you want it to be in float mode.
Heathers, I just broke that.
Okay, make sense? On a couple other tricks. So like what if we want to look at the graph of this thing? So when you're graphing, remember you always, whenever you put a function in y1, don't just hit graph. It's always better to go zoom 6, zoom standard. Get it back to the standard window first. That doesn't look very good though, right? So we're going to want to do some zooming on this. You guys know all the tricks for zooming on these guys? Do you know about Zoom Box?
Yeah.
Zoom just changes the window size for the graph. Okay, try this. This is really a good one. If we go to Zoom and we go Zoom Box, which is option number 1, this is really cool. You can define the size of the window by anchoring the upper left and the bottom right. So we could like go up and to the left very slightly. And if I hit enter, that's going to become the top left of my screen. And now I can define a box like so. Well, I don't want to be there though, do I? Whoops, let's start this over. I'm going to quit. Because I want to be over by 4, don't I? Right? So I'm going to make my box go,
Oh, yeah, you do.
right, I'm going to make my box go, I'm going to start it, there's 1, 2, 3, 4, so I'll start it like over here. Hit enter. I'll just drag out a little box, like so. You can hardly even see the box, but look what happens if I hit enter. Okay, there's the function, and that's 4 right there. Okay? So now if I trace, look what I can do. I can trace along this function, and I'm focused on the part that I'm interested in. Everybody see that?
So 4 is that like moving dot?
So 4 is, watch what happens when I get near 4 here. It skips over 4, and that's one of the problems with tracing on these things is you don't really have any, you don't have very granular control of where the thing goes, right? Okay, but this allows you to trace in intervals where you want to. Now I'm going to go back and show you something else. I'm going to go back to I'm going to go zoom 6 again. Zoom 6. We'll go back to that screen. Another approach would be to say, okay, well, it looks like maybe my upper limit I'm going to make 1, and my lower limit I'm going to make something like -0.1. I always like to make it slightly below the x-axis so I can see it, but I could go in and manually create a window. So my x minimum I'm going to do -3, and my x maximum I'm going to do +3, not -3. Oops, darn it. and my x max, I'm going to do 5. So I'm just going to manually create a window that makes sense. For my y minimum, I'll go negative 0.1 up to y maximum of 1. And if I hit, I can even choose what the scale is going to be. Like now I'm going in increments of 1. What if I want to make that increments of like 0.1? Look what it does if I do that. Increments of 0.1 for both x and y. Screwed something up.
Well, no,
Oh, my answer was, what was my answer on this one? 0.25? Oh, well, what did I do? Oh, I went from negative 0.1 to 0.1. I want to go 1. Okay? You see what I did? So I made the window go, oh, I'm not recording, yeah, I am. So I made the window go from 3 to 5. Those were the x minimum is the left edge of the window, x maximum is the right edge. And vertically I went from a y minimum of negative 0.1 to positive 1. Okay? Another way that you can sort of custom define a window. A lot of being able to use a graphing utility well is just having some facility with knowing how to do stuff like this. We're getting some practice, like organizing it so you can find a good window. So once again, though, you're going to run into the dilemma here where if you're just using a trace to evaluate your limit, you're kind of at the mercy of where the ant steps happen to be. Now this one actually, because it's centered on 4, he actually tries to step on 4. Notice what happens to the y value when he steps on 4. It disappears. How come?
There's nothing.
Because there's nothing there. So that's the calculator's way of telling you that the function is not defined at 4. Okay? Here's another little trick though. If you want to have better control of where the ant is, you can do this. You can just say, you can type in a value. Like I could type in 3.9, enter, and look what it does. It puts the ant at 3.9. You know about that trick? Okay? So if I'm trying to evaluate something close to 4, why wouldn't I do something like 3.999999, go out there a whole bunch of 9s, and hit enter, and what's it tell you? 1/4. Okay, I could do that on the left side, and I could do it on the right side, 4.0001, and they agree. So the value of the limit is 1/4, because I can see that the limit is, he's approaching continuously from both sides. Okay, make sense? So that's a good tool also. Okay. So here's kind of where we left off yesterday, though, right? We were looking at some weird examples where an ant's walking along. Just a quick reminder, we said in this case right here, even though the value of this function at -1 is equal to 4, the value of the limit as x approaches -1 is 3, because remember, that's where the ant would anticipate stepping, right? If you don't get there, that's where you think you're going to be. We ran into a problem, though, when we looked at problems like this guy right here, where there's a break in the function, and we're approaching different values from different sides. That blew up the limit. We can't have a regular two-sided limit in that case, because approaching from different sides gives us different values, and there can't be a preferred direction, right? In math, there's no rationale where that would make any sense. You have a preferred directionality. So we had to come up with a different scheme, and remember we decided here that we could do one-sided limits. By using the notation, if I put a superscript of a negative or a plus after the value of x that I'm approaching, that prescribes a direction. So if I say something like the limit of f of x as x approaches a minus, that implies from -infinity, so from the left. So the limit from the left would be something, and the limit from the right would be something. And they might be different, they might be the same. In this case, they're the same. In order for the regular two-sided limit that we've talked about up until yesterday to exist, all we got to say is that the two one-sided limits have to exist and they have to agree on the same value. And that's now how we've kind of amended and tightened up our definition of a limit, okay? All right, so we said a limit didn't occur there because the two one-sided limits did not agree, right? So we're going to compile a list now of the kinds of places where limits fail to exist. They fail to exist if there is a break in the function, we could say, right? Where the two one-sided limits don't agree. What about something like that where we've got a vertical asymptote? Even if the behaviors, if the asymptotic behavior from the left and the right is the same, and what I mean by that is, if we approach the value of 2 from the left, the function goes to positive infinity, and if we approach the x equals 2 from the right, we go to positive infinity. Is positive infinity a reasonable answer for a limit? It's really not, is it? Because a limit has to be a number, and infinity is not a number, right? So does it make sense then that this would be another kind of place where a limit would be undefined if we have infinite behavior there, if we have a vertical asymptote, okay? And it makes sense because the ant could never point to a place where he's going to go. That's very different from a situation like this, isn't it? Where the ant approaching from the left and the right would agree that there's the place where they anticipate going. Well, if they're climbing up this peak that just gets steeper and steeper and steeper all the time, where they're going to go is always up there, right? There's never a place they can point to. So that's another kind of place where limits would not be defined. Okay, so we'll come back to that in just a second. So limits that fail to exist. We've got one type would be, one type is different right and left behavior. So a break or a gap in the function. Okay. Another type is unbounded behavior. We have asymptotic behavior. We'll add one more here at the end also. It's kind of a weird one. Okay. All right, so let's go back and just get a little bit of review. How about something like this? Let's just answer at least most of these questions. So what is g? Here's our function g. It's a piecewise function, right? So it's got different behaviors over different subintervals of the domain, right? So for values up to +1, for values of x less than 1, it looks like it's just some linear function, right? With a slope of 2. For values of x greater than or equal to 1 and less than 3, it's a constant linear function, right? And for values of x greater than or equal to 3, it looks like it's a parabola. Okay? So you've seen, remember stuff like that, piecewise functions? You'd write it something like this, and there'd be 3 rows on there. Right, remember that stuff? Okay. Not that that's hugely important to us for this example, but we'll talk more. We'll do more of those soon. So what is g of 1? Before. How come?
Because that's where the point acts.
Okay, yeah, because that's a closed endpoint, so that's where the function's actually defined. Now, at the coordinates 1, 2, that's an open endpoint, and so that's a hole in that part of the function. Does that make sense?
Yes.
Okay, so g of 1 is equal to 4. Good. What's the limit of g of x as x approaches 1 from the left? That's 2, isn't it? Okay, so that's 2. What's the limit of g of x as x approaches 1 from the right? 4, because the ant anticipates stepping there from the right. Okay, so that's equal to 4. What's the limit of g of x as x approaches 1? There isn't one. How come? Because those are different, right? So it's not defined. So one way we can say that in math, there's a million ways to say it, but a lot of times, we'll do any, doesn't exist. Okay, does not exist, yep.
I had a question for C.
Mhm.
If the hole is closed, so it's not a hole, it's a point, then how does the limit equal 4 if it's a closed point?
Okay, somebody else answer that. So the question is, let me restate that. So the question is, if this is a closed point, how can the limit be 4?
Because isn't the limit not what it actually is, but what you're predicting it to be?
Exactly. So as far as the limit's concerned, we don't care if that's open or closed, it's irrelevant, right? Because it's just the behavior, it's what they anticipate stepping on as he approaches from the right, okay? And whether or not he actually steps there is irrelevant as far as the limit is concerned,
All right.
okay? G of 3.
It's 1.
1, good. What's the limit of g of x as x approaches 3 from the left? 4, good. You guys see that? Okay. What's the limit of g of x as x approaches 3 from the right? 1. What's g of 4? 2. What's the limit of g of x as x approaches 4? 2. Do you see that? Okay, that two-sided limit exists because the limit from the left and from the right are the same thing. They're both 2. Okay. Good. All right, so okay, yeah, this is kind of cool. I'm gonna build this one up. There's another weird kind of. How much time do we got? What do we have? Oh, man, not much. I might have to do these. Okay, I pre-built this on Desmos, so we'll just throw these up. You all know what the sine x looks like, right?
Yeah.
Okay. There's sine x, right? Okay, what's sine of 2x look like? What's that going to do? And this is really, I want you to, okay, this is one where you got to focus really hard on this, because this is, you're gonna have a breakthrough here in a second. I want you to think, not just memorizing what you did in trig here, I want you to understand why it is the way it is. What is the sine of 2x going to do? It's going to change that, but is it going to, really there's two reasonable things we could expect it to do. Is it going to stretch it out by a factor of 2 or compress it by a factor of 2? Stretch, maybe. Hold that thought. Think what a sine function does. Sine, like any function, it's like a machine. You're going to feed it inputs and it's going to spit out outputs, right? Okay. If I feed a sine function a value of pi halves, what's it going to give me back? Well, sine of pi halves is 1. Good. So let's, like if I do the point, kind of another cool little trick, I could do the point pi halves. And I've already defined the function up here, f of x is sine x, so I could just do f of pi halves, and there's my point, right? Let's make that black. Okay? Make sense? So the sine doesn't really care where the input values come from, right? We could have a composition of functions where we have some interior function that's manipulating the values of x I put in there. The sine function doesn't care. It just knows that when I feed it pi halves, it's going to give me back a value of 1, because that's what sine does. That's the pattern it fits, right? So what if the interior function is a 2x? What value of x would I have to put in there so that sine is seeing the angle pi halves? In other words, 2 times what is pi halves? Pi over 4, right? Does that make sense? So we should expect, if I put in pi fourths here for x into g of x, that's when I should get back a value of 1. Agree? Okay. So what did that do then? Well, look where it puts it. I'm going to make that green so it matches. Okay, so if I turn on sine of 2x, it compressed it, it didn't stretch it. How come? Because we could think of multiplying the input values by 2 as accelerating the argument of the sine function. It's accelerating the pace at which the sine function is getting its angle that I'm feeding it. Does that make sense?
Yeah.
Okay? So if I did something like sine of x squared, now just think about this. What do you think that's going to look like? It's going to be a little more complicated, isn't it? Because 2x is linear, right? That compressed everything by a factor of 2, because any x value I put in, it's just going to increase it by a factor of 2. X squared is nonlinear, right? For what values of x is x squared going to increase the angles that sine sees? In other words, what squared, if I square a number, when does the number get bigger than what I started with, the output? 2 would be an example. So would 4. Any number bigger than what? Than 1. Everybody agree? So for values bigger than 1, it's going to have the effect of compressing the waves because we're going to be accelerating the rate at which the sine function sees its angles. For values less than 1, though, it's going to do the opposite, isn't it? Right? Because like 1/2 squared is only 1/4. Okay? So does this make sense? If I turn this thing on, it's going to look like that. Right? For values less than 1, it's going to stretch it out, but then once you get beyond 1, it's going to start to compress it, and the further you get, the bigger you get, like 10 squared is 100, right? So by putting in a value of x equals 10, the sine function is going to have to have gone through an awful lot of cycles to get up to 100, right? Okay? So what about the bottom one? That's a weird one, right? 1 over x, reciprocal function. So let's do the same kind of thinking on this. For what values of x is this one going to accelerate the rate at which the sine function is seeing angles?
Anything below.
Smaller than 1, right? Because if I take the reciprocal of like 1/10, I get 10. If I take the reciprocal of 1/1000th, I get 1 billion, right? So that's going to do a weird thing, isn't it? As x approaches 0, the value of this angle is going to approach infinity, right? That's a pretty bizarre concept, right? So think about this thing. All these graphs up here, if an ant were to walk along these graphs, he would walk some finite distance between any 2 points on the graphs, right? How far is an ant going to walk if he tries to walk along the graph of sine 1 over x from x equals -1 to +1? Infinitely far, isn't it? Because the sine function is going to have to go through an infinite number of cycles between -1 and 1. Right? So here's what that looks like. Right? So does it make sense then that we could not define a limit for a function like that as x approached 0?
Yeah.
Right? Because as we approach 0, this thing starts to just get more frenetically bouncing back and forth. And it doesn't get better. It just gets worse as you get closer to 0, right? So there's another category of function, and this is a weird one. You don't see these very often. But that's another category of function where oscillating behavior, where limits are undefined. Okay? Is that? Yeah, there it is, oscillating behavior. Okay, so you should be able to tackle that assignment. If you have any questions, first thing we'll deal with on Tuesdays, we'll take any questions, we'll pull up some problems if there was some you had trouble with on the assignment. We'll talk about those in class.
Elizabeth
Okay.
Holden to the attendance office.
Have a great weekend.